This lesson deals with the solution to Exam 2. You can find this exam solution near the end of the ECE201 ebook. This exam was 4 problems long. Each was worth 25 points. This was the actual exam that I used when I taught the course recently, and based on the average and standard deviation, I did the following curve. From 85 to 100 was an A, 70 to 84 a B, 55 to 69 a C, 40 to 54 a D, and then less than 39 not passing. In problem number 1, you were given a circuit that contained only resistors and current sources, and you're asked to write the node equations using the inspection algorithm of Chapter 3. Okay, I have 2 nodes, V1 and V2, so I have a 2 by 2 matrix. I indicated this here in the test with blanks for the entries. I just wanted you to go look at the schematic and write the answers in. So at node number 1, which is associated with row 1, column 1, I'm going to add up the resistances connected to this node, but as conductances. So 1 over 1K plus 1 over 333.3. I did it on my calculator, and that turned out to be 4 millimos. Between nodes 1 and 2, there's a 330 ohm resistor, so the reciprocal of that, negated, is what goes in row 1, column 2. The currents entering node 1 will be on the left-hand side of the equation, in row 1, column 1 of our current vector. I have 100 milliamps entering and 25 milliamps entering, so that's 125. So that's my first equation, and the 2 unknowns, V1 and V2. Go to node 2, add up the conductances at this node, so 1 over 1K plus 1 over 333.3 is equal to 4 millimos. What's between nodes 2 and 1 is going to go in row 2, column 1, and that's going to be 1 over 333 negated, so minus 3 milli. The currents entering this node are going to be equal to a minus 100 milliamps plus a minus 25 milliamps. So a total here of minus 125 milliamps. This is worth 18 points. I did get partial credit here. I gave 3 points for each entry that's here. Then based on the matrix that you had, could you solve for node voltage 2 using Cramer's rule? If you recall, the technique is to take the determinant of the conductance matrix, that's our denominator. The numerator will be that matrix with column 2 replaced by the left-hand side of the equation. So whatever you had here, whether it was right or wrong, I just followed the work on this one. Then the product of these two, so 4 milli times minus 125 milli, which is turned out to be minus 500 micro, minus the product of these two, which is a plus 375 micro. Product of these two is 16 micro, and then minus the product of these two, which would be a minus 9 micro. And the ratio of these two numbers of 125 to 7, with a minus sign, is a minus 17.857. And this is worth 7 points. And I gave partial credit for getting the numerator right and the denominator right. Had 3 points here, 3 points here, and then 1 point for getting the final ratio. And this is problem number 1. Problem number 2, given this circuit, could you find the current I2 using superposition? If you recall, the technique is to set all of the sources equal to 0 but 1 and find the response due to that one source, and do that for all the sources. So I'll call this I2 prime. Due to the first source here, the 9 volt, well, they can start in any order, and setting the 4 milliamp equal to 0 is setting it equal to an open circuit. If I knew the voltage across this node to ground, then I could find the current in this loop. So let's do that with a voltage divider. So I have 9 volts. I have the 1K in series with the 2K. That's 3K in parallel with 2K. Can't ignore this. This is actually loading the circuit down. Voltage divided with a 1K. So here's my 2K in parallel with 3K. Voltage divided with 1K. Did this on my calculator. Product over the sum was 1.2K, and then adding 1K to that is 2.2K. And I got 4.909 volts. So the current that's flowing in this loop then would be the voltage 4.909 divided by the total resistance of 3K, and that's 1.636 milliamps. This time I consider only the current source of the 4 milliamps and set all the other sources equal to 0, just 1 here. So I'm going to short that, and then find the current I2 due to the second source. Now the short circuit here is really putting the 1K in parallel with the 2K, and the product over sum would be 2/3 of a K. And then I've got the 1K here and the 2K. I just kind of redrew this part, sort of like that. So I've got my 4 milliamps back to ground. And really what I've got is a current entering a node, and then it splits. Some goes this way and some goes this way. So I can use my current divider. The current in the 2K resistor, which I want to solve for, is going to be equal to the other resistance, if we do the resistance current divider, which would be 1.666 K divided by that plus 2K times the 4 milliamps, and that's 1.818 milliamps. And then we're going to add the two results together. And it's 3.454 milliamps. Give 12 points for the first part of superposition, same for the second, then if you could add the results together. Didn't give much partial credit for the errors in these individual parts. These are very basic circuits. This is problem number 2. In problem number 3, you're given a circuit and asked to Thevenize the circuit with respect to terminals A and B, and then to use that Thevenin equivalent to solve for the current I sub x. Recall from our algorithm, we remove the load, so we're left with this circuit. We're going to find the open circuit voltage, and then we're going to find the resistance looking back with all the independent sources set equal to 0. Here again, I wrote my steps on the schematic. With this being an open circuit then, what I've got is a voltage divider on this side from node A to this, called a reference point. So I get a voltage divider of a half, so it'll be 2.5 volts. On this side, I've got the 500 milliamps going into the 6 ohms, so it's going to create the product of those two, which is 3 volts. So my open circuit voltage then is node A minus node B, if you think about this as a reference node down here. So 2.5 minus 3 is a minus half a volt. Our second step with Thevenin's theorem is to set all the independent sources equal to 0, so short a battery, open a current source, and look in the terminals A and B. I have these two in parallel now, which is half the value, or 4 ohms, and that's in series with 6 ohms, so I get 10 ohms. So now I can represent my circuit, my Thevenin equivalent. You have to remember here now that we were Thevenizing with A with respect to B, so the plus sign on the Thevenin voltage will be near A and the minus by B, but my value was a minus half a volt, and my Thevenin resistance here. Now the current flowing in this direction would be the Thevenin voltage divided by 10 ohms plus 10 ohms. So I got a minus a half a volt divided by 20, and that's a minus 25 milliamps. I graded this as 9, 8, and 8 points, and didn't give any partial credit. This was either right or wrong. This one was calculated based on what these two were. So if these were wrong, I just followed the work through and found this current. And this is problem number 3. Problem number 4 is a design example. I took an old Sony Discman CD player. It was actually a model D131, which operated on 2 AA batteries. And I removed the batteries and put a power supply in. I was able to monitor the current that the CD player was drawing. When the CD player was seeking out a song, so the motor spinning at its fastest speed, it was drawing around 420 milliamps of current. What I want to do is I want to use the CD player in my car, which has a 12-volt system. If I put the 12 volts across the CD player, I probably will burn it out because I'm way beyond its normal operating voltage. So what I need to do is step this 12 volts down to 3 volts. We could do that with a voltage divider. Let's draw a schematic of what we got here. So I've got a 12-volt car system. I'm going to use a 15 ohm resistor. I'm going to pick the value of R2 such that I have 3 volts across the CD player when I'm drawing 420 milliamps. You can think of the CD player as if it were a resistor of 7.14 ohms. Now it really isn't a resistor, but under these values of voltage and current, I can recreate the same conditions in my circuit. All right, what do I know about the conditions that I just described? Well, let's just label them all in the drawing. If I have 12 volts here and 3 volts here, I've got to have 9 volts across here. If I have 9 volts across 15 ohms, I got 600 milliamps of current. So the current that's entering this node is 600 milliamps. What's leaving is 420 plus whatever's left over, and that'd be 180 milliamps. So if I know the voltage across R2, and I know the current, I can solve for the resistance. And it turns out to be 16.66 ohms. This was graded pretty much right or wrong. It's given a value of 9 points. I was taking the measurements on the CD player and noticed that the current dropped when the songs were playing. It went from about 420 milliamps to 250 milliamps. You can think of that now as if it were a resistor. I got 3 volts across the CD player, but now I'm drawing a lot less current. What's going to happen to the voltage across this CD player when this happens? So I've got a fixed resistor here of 15 ohms and now 16.66 ohms here, and now my CD player looks like it's a different resistor value. So let's analyze the circuit. I got a voltage divider. So 12 in parallel with 16.66 is voltage dividing with 15. Turned out to be 3.809 volts. So no matter what you calculated here, I followed the work through to grade this one. It was worth 8 points. What's happening now is we've changed our voltage across the CD player from 3 volts to 3.8 volts. Will that destroy the CD player? Probably not. But on most electronics, if you look on the back, they usually give a range of voltage for operation. You may want to do that when you look at doing a design like this. Now to know the value of the resistors, the last thing I do is pick the wattage of the resistor. It's the last part of this design. Let's look at the two scenarios that we had. We had 9 volts across R1. It was 15 ohms, so V squared over R, 5.4 watts. The resistor R2 had 3 volts across it with a value of 16.66. That's 540 milliwatts. But then as the load changed, the voltage across R1 now is going to be 12 volts minus my new value across the CD player, which is 3.809. That's 8.191. Squaring that and dividing by the 50 ohms, I now get 4.47 watts. So much more power consumed in this case. So if I were to pick a 5.4 watt resistor, then this case would be safe. We'd get a lower wattage dissipation. For the resistor R2, likewise, I've now got a different voltage across it, so it's 3.809. When you square that and divide by the 16.66, I get 870.5 milliwatts, and that's larger than what I had before. So the worst case is this one and this one. So if I were to pick my resistors with at least this kind of a wattage rating, then it would handle these other cases without being destroyed. This is our design for a CD player being plugged into an automotive 12-volt system. And this is exam number 2.